Good morning or evening or afternoon or whatever time it happens to be where you are. We've got a British invasion for you here today on TinyML Talks. So my name is Daniel Sitanaika, and I work at Edge Impulse. I'm the founding TinyML engineer. And joining me today is Eben Upton from the Raspberry Pi Foundation, who's also a Brit. And he's joining us from the other side because I'm in the US, he's in the UK. So we've got a sort of pan global British experience for you. So Evan's going to be talking about inference with Raspberry Pi Pico and RP2040. So it's super exciting. There's a lot of buzz about today's talk. So before we kick off, I want to thank all of our sponsors. So we've got ARM, DeepLight, Edge Impulse, Maxim Integrated, Kixo, Reality AI, and SynSense. If you're interested in potentially sponsoring the TinyML Talk series, drop an email to betty@tinyml.org for more info. Next up, on Tuesday, March 16th, we have a talk from Vijay Janappa Reddy, who's an associate professor at Harvard, and he's going to be talking about TinyML Perf, deep learning benchmarks for embedded devices. So Vijay's a great speaker. Definitely don't miss that one. So I wanted to take a few moments today to talk about the TinyML Summit, which is fast approaching. It's going to be March 22nd to the 26th. So this is going to be a fantastic event. We've got some amazing speakers, amazing panels, and I definitely recommend attending. I think we have around 2,000 folks have signed up so far. So if you're interested in attending, please head to tinyml.org/event/summit2021 and join us. It will be really good. I'm going to be there. Hopefully get to meet and chat with some cool people. So here's another slide on the summit, just showing how many attendees we've got expected and the growth that we've had in the last 3 years. You know, I mean, the first summit, we were all in one room on one of the Google campuses. And this year we're going to be 3,000 people online, 300 different companies. So it will be really great. So our summit sponsors here are sort of too numerous to list, but if you're interested in sponsoring the summit, drop us an email at sponsorships@tinyml.org and yeah, help us put on this awesome event. So without further ado, I'm going to introduce Eben. So Dr. Eben Upton is a founder of the Raspberry Pi Foundation, a former distinguished engineer with fabless semiconductor manufacturer Broadcom Incorporated, and founder and former CTO of mobile games middleware developer IdeaWorks 3D Limited. He holds a BA in physics and engineering, a PhD in computer science, and an MBA from the University of Cambridge. And now I'm going to hand over to Eben, who's going to present his slides.
There we go. Thank you very much, Daniel. So yeah, I'm another bit of the British invasion. The British are coming. The British are coming. I saw in the chat we have a British person in Israel as well. So we really are. I think we really are pretty uniformly distributed around the world here. You know, we're spanning at least what's that? That's 10 or 11 time zones. So yeah, so today, so I'm Eben. About 13 years ago, I found, now it's an awfully long time, I founded a thing called the Raspberry Pi Foundation here in Cambridge with the aim of getting young people, this very narrow parochial aim of getting young people involved in computers. I was involved in computers when I was a young person. There was a little bit, I think, of a dwindling of young people's enthusiasm for computing during the 90s and the early part of this century. We saw that at Cambridge in the disappearance of our talent stream. And Raspberry Pi exists as a charitable foundation to fix that problem. And the way that it fixes, one of the ways it fixes that problem is through its trading subsidiary, Raspberry Pi Trading, which is what I run, and we do that by making little computers. Now, for a long time, we've made, I hope many of you know a little bit about the kind of computers we make. We make a series of little Linux boxes at price points ranging from $5 for the very cheapest up to now $75 for our most powerful device. But they have a lot in common. You know, these are all devices. They run Debian. When using our operating system, they run Linux. They run a Debian userland which is derived from Debian, and they have a very PC kind of feel to them. You plug them into a display, you plug a mouse and keyboard into them, and you can do all sorts of stuff on them, but they are PCs. They do get used as embedded systems, but they probably come from that kind of big world. Now, an interesting thing's happened recently, which is we launched something new. So if I present my first new slide. So we did this in January. So nearly 2 months ago now, we released a thing called Raspberry Pi Pico. So this is another product with the name Raspberry Pi something, but it's very different from every other Raspberry Pi we've made in that it's a microcontroller platform. So this is not a Linux box. This is a microcontroller platform, and therefore it's something that takes us into this world of microcontroller software, and in particular this world of very low power, relatively low performance edge inference. So Raspberry Pi Pico launched it on the 21st of January. It's $4, so it's, I think, also, as well as being probably the lowest end thing we make, it's also by $1, the cheapest, the lowest cost thing we make. I'm generally banned from using the word cheap to describe things. I'm supposed to describe things as being low cost or extremely good value, but it is the cheapest thing we make at $4. The interesting thing, though, about this board is for the first time, this is a piece of board level hardware that's built on a piece of silicon level hardware that was designed here at Raspberry Pi. So rather than going out and finding some merchant, there are a lot of fantastic merchant microcontrollers out there, but it wasn't felt that it was possible to offer, and there were a lot of fantastic microcontroller development boards built on top of that merchant silicon. But to do something interesting and differentiated in a lot of ways, to do something which was differentiated from a performance standpoint, from a feature standpoint, from a cost standpoint, we really felt that we actually needed some Raspberry Pi silicon inside this, and thus the chip in the middle of that. So it's a board with a Raspberry Pi logo on it, in the middle of it, a chip with a Raspberry Pi logo on top of the chip. And this chip is called RP2040, and it's probably the first in a line of interesting microcontrollers. And you can really see on some level, you can see Raspberry Pi Pico as being just a breakout board for this. Nice thing about how designing your own chip, of course, is that you can co-design it with the board. So this is a very, very nice simple board. If you look at the tracks on that board, they all look awfully neat. They all go out to pads. And of course, that's because the board itself was co-designed with the package, and the package was co-designed with the silicon that goes inside the package. So on some level, this is just a breakout board that gets the GPIOs out of that chip, brings them to some pads on the edge. They're both through-hole pads and castellated pads. So this is at the board level, while the chip, we're very much hoping other people will design. I've got some examples later. Very much hoping people will design that chip into their own hardware. The board itself is designed to be used as a module. So with castellated, this thing has castellated edges, so you can solder it down onto a board. And it's in fact supplied in a reel. So it's supplied in the packing format for this is reels of, I think, 600 at a go. And these big chunky, I mean, you've seen components, you've seen surface mount components on reels before, and they're kind of that thin. This thing is like a big sort of, I don't know, like an ammunition belt or something, full of computers. So it's a breakout board for the product. It's designed to be used as a module. It does have quite a nice power chain on this. It has this buck boost power chain on there. That means you can power it from pretty much everything. And so we kind of see this. You can power it from a couple of AA cells. You can power it from a lithium cell in pretty much any state of charge. You can power it from USB, and regardless of so it's a buck boost converter. So you can feed it less than 3v3 volts, and it'll push that up to 3v3 volts. You can feed it more than 3v3 volts, and it'll regulate it down to 3v3 volts. So this is really something that we're hoping will find its way. The big Raspberry Pi product finds its way into all sorts of exciting places. We have big Raspberry Pis on the International Space Station. We have big Raspberry Pis that have gone to the bottom of the ocean. We have ones that have overwintered in Antarctica taking pictures of penguins. So this is really something that we're hoping will find its way into all sorts of places. And one of the things that we're hoping that this board will do when it's in all sorts of places is to do edge ML inference operations. This is something that's been in development, obviously, for an enormous length of time. It's enormously more time-consuming to enter this world by first designing your own chip than it is to go out to DigiKey and buy some chips and put them on a board. So this is something which has had a very long gestation. And at the start of that gestation, really, I think you had your statistics about how rapidly this community has grown. that window of time you described there is only a tiny fraction of the window of time that this platform has been under development for. So this is not a platform that was designed for doing inference. I think probably seeing the inference things people are doing with it probably might give us some thoughts about things we might do with future platforms, and I might speculate on a couple of those. But this is a platform which is accidentally, I think it is showing promise, and I'll have a couple of little benchmarks later on. I think it's showing some promise as an ML platform. I think it has some interesting differentiated features that happen to be relevant to inference, but it is an accidental, I guess like most microcontrollers actually, it's an accidental inference platform rather than a designed inference platform. So let's look at RP2040 in a little bit more detail. First, in-house silicon from Raspberry Pi. It's a dual-core, symmetric dual-core microcontroller, which is a fairly rare thing. Has a couple of ARM Cortex M0 Plus. And M0 Plus is an interesting core. It's ARM's lowest energy core in terms of energy consumed per instruction executed. It has the shallowest pipeline of any ARM core, so it has a two-stage pipeline, and that contributes to the low energy of the design because you have fewer pipeline latches to clock stuff through. It also provides a little bit of a performance increment over Cortex M0, which is its immediate, its three-stage pipeline immediate predecessor. Nominally, being only two-stage pipeline puts a little bit of a cap on the frequency that this design will operate at, but the other interesting thing about this core, about this chip, is that it's implemented on a relatively modern process node. It's on a TSMC 40 nanometer process node, which is fairly aggressive by the time. It's about a decade-old node now. But for a microcontroller, it's relatively aggressive. That's let us push the clock speed all the way up. So it's nominal operating voltage of 1.1 volts. We rated 133 megahertz. It's shown enormous overclockability in the field. There are very, very few of these parts that won't run at 250 megahertz. I'll talk a little bit later about possible higher clock operating points for this design. But even at 130, a pair of cores at 133 megahertz, which can issue an instruction per, which have been configured with the single cycle multiplier option, and can issue an instruction per clock. That's an awful lot of scalar MIPS. And actually, when you take those scalar MIPS and you apply them to ML workloads, you get quite respectable performance. Even though the M0 Plus is, I think, generally a core that you would associate with lower end microcontrollers. Quite a lot of SRAM on the device. So we've put a quarter of a megabyte of SRAM on the device. We sometimes talk about this being an off-leading diagonal product. You tend to get M0 Plus designs, you tend to get designs with small cores that have relatively little RAM, and you get designs with large cores, M3s, M4s, M7s, that have large amounts of RAM. You don't tend to get these designs that have a lot of one and not so much of the other. Particularly useful for machine learning applications because it lets us buffer a lot of data in memory. For relatively small models, I've got a couple of examples later on. For relatively small models, it lets you store all of your model coefficients in RAM, which gives you a very very simple programming environment. Once you blow past that RAM, things get a little bit more complicated, and that's where you run off the end of the optimization work we've done so far. Partly because it's on a modern process node, we've chosen to go with a flashless architecture. So this is a stateless device. This has no non-volatile, has no one-time programmable memory, has no E2, it has no flash, it has no non-volatile storage at all on the die. And therefore it relies on an external flash. In this picture here, you can see it above and to the left of the main chip. On the Pico, that's a 2 megabyte QSPI flash. That means that flash is far away from an architectural perspective. It's far away. It's relatively slow to execute from. And it gives us this interesting world where we have blinding speed out of quite a lot of SRAM, and then we have more modest speed for larger workloads. So to some extent, getting good performance out of an RP2040 based product or application is about partitioning your workload between, it's finding your hotspots, making sure they live in RAM, and to the extent that you have hotspots that are larger than RAM, as we find with some large machine learning models, finding ways to pipeline away the latency of getting that data into RAM before you work on it. It has what we call a simple deterministic bus fabric. The idea here was to create a device which had a lot of performance, but also where a programmer using this device could get at that performance. What that's driven us to is a bus fabric. We have a crossbar in the middle of this chip. So we have a rather deluxe, for a microcontroller, we have a rather deluxe bus fabric, which is a fully connected crossbar, which allows any master and any slave to communicate with each other at full rate if uncontended. The idea here really is, to let people, to avoid having to margin against, to avoid programmers having to margin against non-determinism. Obviously, nothing's non-deterministic in chips, but the determinism can be so complicated that it might as well be non-determinism. And the idea really is to give programmers the ability to go right up to the edge of the cliff, where one more step you'll fall over. And we have some lovely, particularly video demos of this thing outputting video to VGA and DVI displays, which are absolutely at the edge. And if you insert one more cycle in various places, the thing falls over, and you can understand where that cycle is. And it's just a wonderful environment to develop software for. It's a wonderful environment to optimize for. And that's where we are at the moment with the ML work. It's a wonderful device to optimize for because you can make continuous forward progress because of this bus architecture. We've tried to put as rich a peripheral set as we can into the design, so we've put a number of hard peripherals, the usual hard peripherals, UART, SPI, I2C, PWM, has a lot of PWM channels, which is kind of fun for motor control applications. Put USB 1 natively on there. A lot of that's about the ease of use from a programming point of view, so this is a device that you can plug into a PC, appears as a mass storage device, drag a program onto it, it reboots and runs. So really that's something you couldn't do if you didn't have USB 1 on there. But from an ML point of view, it also opens the door to acquiring data from the very, very large number of peripheral devices which export a USB interface. So one thing I'm hoping we're going to see in the next couple of months is the first USB webcam image recognition demos on this platform. It's not something that's appeared yet, to the extent that people are connecting cameras to these. At the moment, it tends to be parallel or SPI cameras being connected onto the GPIOs, but I think we are going to see an interesting world of people using webcams and other USB attached sensors, USB attached microphones and stuff as their input for ML. I guess the last thing, and the thing that people probably talk about most with this design, is a thing called PIO. This is our programmable I/O world. This allows us to simulate. So I talked about DVI output, talked about VGA output. There is no DVI peripheral on this device. There is no VGA peripheral. There's no SD card peripheral. There's no I2S codec peripheral on the device. But we have demos of reading, streaming video in from SD cards, decoding it, putting it on a DVI display, and outputting audio to an I2S codec. All of that is done using this subsystem that we call PIO, which I'll talk about in a moment. It really is kind of, I guess, bit banging. Lots of us, I guess, have written probably some of my earliest, in fact, the earliest Raspberry Pi from 2006, the earliest thing I would call a Raspberry Pi, was a little computer that bit banged video out of an AVR, out of an Atmel AVR8 chip, and bit banged composite video onto an analog television. We've all had that experience of finding a microcontroller that doesn't quite have the peripheral you want, and therefore you end up dedicating, if you have one core, really most of the compute resource on the device, or if you have one of these symmetric or asymmetric dual cores, dedicating one of the cores to bit banging pins. What we wanted to do was give you 2 cores on the platform. If you absolutely must, use one of those cores to bit bang pins, but we also wanted to give you a special clever state machine that we, in our mind, can comprehend 80, 90, 95% of the bit banging operations that we're aware of, in the hope that they will also comprehend some of the operations that we're not aware of. And I think we've seen some evidence since launch that that's worked out. Talked a lot about RP2040 in the context of Pico. Of course, the ambition here is not to just to produce development boards, it's to produce chips. We've had some fantastic engagements with third parties already around this. We did some pre-launch engagement with Adafruit, SparkFun, Pimoroni, and Arduino to get RP2040 boards ready to go. The first of those are out. There is one SparkFun board and one Pimoroni board out, and we are imminent. I think we're going to see some more imminently. They're interesting because they bring this. Pico is a very limited board from a machine learning perspective because it doesn't have many inputs, doesn't have many sources of data. The interesting thing is, what we hoped would happen, and what I think we're seeing happen, is that people building boards on top of RP2040. When you've got a $4 Pico in the market, you're not going to compete with it on price. You compete with it by you differentiate yourself through feature set. And what we're seeing is everybody who's offering RP2040 based designs has an interesting differentiated feature set, and I'll call out a few later on that I think are going to be particularly interesting for ML.
So we've got some really good relevant questions here. If it's
Yeah,
all
let's
right,
go for it.
jump in.
Yeah.
Yes. So one of the questions was why aren't there any onboard sensors on the Pico? And it seems like you just answered that.
Yeah, that's it. I mean, it was really about providing the lowest, you could say the lowest cost, but also the most. There's a sort of design philosophy in Raspberry Pi, which is about, it applies to the big products as well. It's about, it applies to the hardware and to the software on the big products, which is where we try to invest is the common ground, the bits that everyone will need, and when we tend to leave the differentiating bits to other people because we're not particularly good at them. And I think we have a low estimate of our ability to make good decisions in this space, and so the kind of cowardly, the prudent or cowardly thing to do is to just focus. So where do we spend our money in software engineering on Big Pi? Spend it in the kernel. We spend it the closest we get to an application is a web browser, which is actually really a piece of middleware. But we tend to spend our time in kernel and middleware rather than up at the application level. And I think that's mirrored in the big Raspberry Pi hardware, and it's mirrored here as well. And to some extent, it's mirrored in the software platform for RP2040 as well.
So in terms of the MCU and the general market, what is it about the RP2040 that differentiates it from other MCUs that are out there? Why would developers be using RP2040?
I think it's got an extremely good price performance point. Obviously, we're not selling the silicon yet, so you don't know whether it has a good price performance point. But the fact that we're building a board on it that we retail for $4 sort of suggests it has a good price performance point. It is very cost effective design. It's that off leading diagonal thing. I think we have a view that lots of integer. What people want is lots of integer performance, lots of predictable integer performance. They're back to this question about determinism. And lots of memory, because lots of memory, time spent not squeezing your program to get into memory is time saved. And obviously, in an advanced process node, memory is pretty cheap. This is a 2 square millimeter die. It's literally, it couldn't. If you made it any smaller, you'd have to start throwing away GPIOs because there wouldn't be enough periphery on the die to fit the pads for the GPIOs. So it's a very carefully balanced design. It's fun, and we've gone to some effort with documentation as well. I mean, it sounds like a little thing or a thing that everybody does, but actually, you look at a lot of documentation for microcontrollers, it's terrible. And so a chap who I'm sure is well known to many people in the ML community, a guy called Alistair Allen, joined us as an employee at the start of last year to focus on making sure that it is a state of the art chip, and we wanted it to go out the door with the state of the art documentation next to it. So we've got lots of power, it's predictable, and then we actually tell you how to use it, which turns out to be an innovation.
That's excellent.
Yeah.
So
sorry. Let's do some more questions.
Yeah, I was going to say one more question, and then maybe I'll let you move on because I think your slides might answer some of these questions. But why is the name 2040?
Yes. Okay. So we made up a naming convention. I've read a wonderful article about Intel's naming convention from the early 1970s when they first started making DRAMs, and they had a naming convention that withstood contact with the market for about 9 months, and it had this here means it's TTL, this here means it's CMOS, this number means that it's a DRAM, this means it's an SRAM, and it's naming schemes are always a disaster. So what will be an amazing triumph for me will be if we make another chip and it fits into this naming scheme. That will be amazing. That would be like 2 chips. 2040 RP2. Well, I mean, the product line gets called RP2 a little bit. So the 2 is dual core. So the 2 is dual core. The 0 is M0 plus. The 4 is floor log to the base 2 amount of memory divided by 16K. So it's
wow.
16 lots of 16K plus a bit. So if you made one with twice as much memory, it would be an RP2050. If you made one with a Cortex M3 in it, I guess it would be an RP2340. And then the 0 on the end is amount of on chip flash. I mean, if we ever took one of these and packaged it with some QSPI flash in the package, we'd probably use that digit there. But that will be, again, some log-based scheme for how much on chip storage. You'll notice that you have to, obviously, as you know, in a log-based scheme, you have to have 0 is special case, because otherwise it's just otherwise it would just be 0, and that third digit would just mean 16K. Yeah, that's RP2040. I don't know what we'll make next. I mean, I guess, you can kind of invent things. What I do think is we're unlikely to ever make anything that isn't dual core, because we're really very obsessed with that idea of having the application core, for general use. I think for machine learning applications, you're going to end up using both cores flat out to run ML. But for other applications, we're quite obsessed with this idea of having a core that manages hardware, hopefully not directly, hopefully a core that manages PIO, which is managing hardware for you, and then a core which runs application code. So I suspect that, and that's thus the kind of RP2 sense to the kind of to the brand, I guess. Make sense?
Yes. Fantastic.
Page of datasheet. I just summarized an entire page of datasheet for you there. This is the chip, though. So this is just to give you an idea. So I gave you some words. This is the picture, which hopefully is worth thousands of them. What can you see in there? What's the biggest box in here? Bus fabric. What do we really care about bus fabric? So this is this big wedge. You can see it has 4 things on the top. It has a DMA engine with a read and a write port. It has a very completely symmetric pair of processors on there. Big slab of bus fabric. And then lots of blocks of SRAM at the bottom. And really the goal here is to make sure that you can DMA at full rate from one block to another block, while one processor fetches code from and reads and writes data to another block, and then the other processor does another block. You have 6. So you've got 4 big blocks. So you've got 4 64K blocks. That's the main memory. You have a choice. You can either put those consecutively after each other in memory, and that's if you want to really do that work to make sure that you can guarantee, as we do with some of our video demos, where you really want to guarantee that you understand the cycle by cycle access pattern of the core, then you can do that. The other thing you can do is you can interleave them at 32-bit granularity, so you can have bank 0, bank 1, bank 2, bank 3 repeat with 32 bits coming out of each one. This whole bus fabric is 32 bits wide, and that means that what you get then is you get a kind of an amortized, you get something that's a little bit more like the way SDRAM works, right? So you get a kind of amortized fastness. So you will contend, and if you can contend, you can set priorities to help you understand what's going to win. But you'll get some sort of, it'll be good. It'll be okay. It won't be quite as good as it would have been if you'd done all the work in terms of partitioning your data, but neither will it be as bad as all of your cores hammering away on one block of SRAM. So we've got SRAM stuff down there. You've got the boot ROM, which has got lots of fun, accelerator functions in it that we went out and paid for. We don't have a floating point unit in the main core, not super relevant to ML. We don't have a floating point unit, so we actually went and paid somebody to develop some really incredible floating point acceleration functions, and we baked those into ROM in the chip. So you're not even, there has no RAM footprint. A, it has no RAM footprint, so it's not occupying RAM, but B, it's also not occupying bandwidth. So if you use our floating point functions, while you're adding 2 floating point numbers together, which takes 50 or 60 cycles, you are not on the bus. You're not on the, you're not contending with the other processor or the DMA engines for access to systems resources. Slate of hard peripherals there in the middle. So over on the left-hand side, you've got your GPIO banks. We've got 30 GPIOs on the chip, of which 26 come out on Pico. You have the QSPI interface, which with a cache in front of it. And then you've got this PIO, these PIO blocks. Now, what's a PIO? Well, this is a PIO. So PIO is kind of it's a little processor, which is very specialized to the task of moving things to and from pins. You have 2 copies of this. Each copy has a little instruction memory. So you write programs for this thing. There's a little language of, I think 7 or 8, I think 8 instructions. You write a little assembly language program, you put them in the instruction memory, and then you have 4 state machines that can go and access that instruction memory. And so you can either you can have 4 state machines all running the same program. So I suppose you load that state machine with a program that that describes how to be an SPI be an SPI controller. Then you can have 4, in addition to the 2 hard SPI cores on the chip, you can have 4 additional SPI cores which are running in the state machines, and then you can have another 4 over in the other PIO. So you could end up with 10 SPI channels if you really like SPI. I think you might run out of GPIOs before. No, you probably just about have enough. Actually, you've got 30, so you need 3. So you just about have enough to have, if you don't do anything else, if you want to be a USB 1 to 10 SPI bridge, you can just about fit that on. Or what you can do, if your little programs are small enough, you can put several of them into that instruction memory if you can fit them all into, and it's very compact instruction encoding. 32 instructions doesn't sound like very many, but very compact instruction encoding. You can put several of those into the instruction memory, and then you can have different state machines within each PIO instance to do different things. So when we show a demo which is driving I2S audio, which is reading from an SD card, driving I2S audio to a codec, and reading from and driving video to VGA or DVI, you have several different programs that are packed into the PIO memory. So PIO memory is kind of a precious resource. How do these things talk to the rest of the world? Well, they talk to the bus via FIFOs, so they have input and output, 4 entry input and output FIFOs, and then they talk to the outside world through GPIO muxing. So effectively you say, oh, I'm going to have these 50, I'm going to do an RGB 555 VGA output. I'll have this pin here be H-sync, this pin here be V-sync, and these 15 pins here be the outputs to my DAC. And so you you can slide this kind of a barrel shifter that lets you take the output of one of these state machines and position it in GPIO world. Over on the right here, you've got, this is what's inside one of these state machines. So you have input and output shifters. So you're effectively pulling things from FIFOs, putting them into these shift registers, and then shifting them out onto pins. You have some scratch registers. You have a clock divider. So you have a master clock that you feed into this, and then you can divide it down. So if you have you're running a UART, you're running a 50 or 115 kilohertz UART on there, you can take your system clock of 133 megahertz and bash that down until it's a little bit closer to the UART rate that you need. And then you have a program counter, and the program counter, so you just step through these instructions and you can branch and you can do all sorts of really alarming stuff. And the lovely thing about this is, like I say, we designed this by trying all of the protocols that we could think of and adding features to it until it could do all the protocols we could think of. Post-launch, people are starting to find devious things to do with this infrastructure. In particular, the DVI example, somebody the other day managed to get double the DVI output performance that we'd got out of our. He got a better program, effectively. He got a better program that he could load into a PIO than we'd ever thought of. And that feels like a good sign, right? So this feels like I think in the datasheet this is described as for talking to cursed serial peripherals you found on AliExpress. And cursed serial peripherals from AliExpress are a powerful source of data for machine learning. So we're quite excited about this, because we do think that in this kind of world of this is glue that can connect input to compute and storage to output, and we do think there's a high likelihood that we're going to be able to interface to random cursed stuff. So yeah, as PIO, we're super proud of that, actually. So we are very early in the ML. I'm happy to answer questions about ML, but we are really, really, really early in understanding how to exploit this device for ML. But we already got a little bit of an idea about where we got lucky, I guess, the good and the bad. Where did we get lucky and where did we get unlucky from the point of view of this as an ML device? What's the good? Well, it's got a high clock rate. 133 megahertz base clock is really, really fast for a microcontroller, actually. You do get some of these crossover, I think NXP call them crossover microcontrollers, right? Things with 600 megahertz M7s in them. But by and large, for a regular microcontroller, that's a decent clock rate. So we've got a good clock rate. We've got dual core, and we've got fully symmetric dual core. And this is great because this means that we hope to be able to partition running a layer of a CNN. We hope to be able to partition workloads smoothly. There's a trivial partition. You don't have a fast core and a slow core, and you're trying to guess how to partition the work so they both complete at the same time. You just partition work 50-50, and they'll both run. And of course, because it's very deterministic, they will both kind of, as long as you manage the memory contention, they will just march through in lockstep, and they will arrive probably within a cycle of each other. They'll arrive at the end of their partition of the work at the same time, and then you can get on to the next thing. And we've got a lot of on-chip SRAM. So for some models, we can fit absolutely everything in RAM. So the keyword, we've done some nice work with Pete Warden at Google on TensorFlow Lite. It's got his keyword benchmark, and for that, we can go and fit all of the model parameters and the test data into RAM, and we see an enormous improvement between putting that in Flash and putting it in RAM. So simple models, absolutely no issue with just squishing everything into RAM. So that's super helpful for us. What's the bad? Well, no SIMD. So this is an M0 plus. It doesn't have even the kind of M4 era SIMD instructions, let alone the stuff that we all know is coming from ARM in the way of future SIMD operations, which are explicitly targeted towards machine learning operations. So no SIMD instructions, no single cycle Mac. Now you have a choice with M0 Plus as to whether to configure it with a 32 cycle multiplier or a 1 cycle multiplier. I don't know who would, it really isn't that big. I do not know who would configure it with a 32 cycle multiplier. We configured it with the fast multiplier. So we do at least have single cycle mul, but we don't have single cycle Mac. And therefore that cuts your dot product throughput down by a factor of 2. So that's a little bit unfortunate. Currently limited. I'll probably add one to the bad, actually. Flash is a long way away. So Flash, and you can see this in the set of benchmarks here, Flash is an awfully long way away. It's at the end of a QSPI bus, so you need to go and send your address over QSPI and then start reading stuff in. So if you find yourself reading, we have a 16K cache in front of that Flash, which is largely intended for instructions. But if you find yourself blowing out that cache, which you will do if you've got model data out there, the Flash is an awfully long way away if you are reading from it on demand. We have a good bit of bandwidth to it, actually. We can run that bus at 80 megahertz. It's 4 bits wide. It's a good bit of bandwidth, many megabytes a second. But if you're using it on demand, the latency is a bit beastly. So I'll put that on the bad list. And then the last one, currently limited sensor choice. We are 6 weeks into this platform, so into the release of this platform. The sensor choices aren't amazing, as some of you in the Q&A have noticed. That's a current issue, though. So we've already found people finding ways. We've already had some great camera demos on there. We're having boards from our partners. We have prospective boards from non-partners. Saw one today from Arducam, which are designed for machine learning. So I think that this is very much a temporary, a temporary situation, but it does limit us a little bit in terms of the data that we can show you. So Pete produced an initial TensorFlow Lite port with some help from Graham Sanderson, who works for us and has led on the SDK implementation. What's interesting about this? Well, stock clocks. So we're running at 133 megahertz. We have a single core, so no work has gone into partitioning the work between the two cores that we have available. And the model parameters are in SPI Flash for large models. So if you look over here on the side, you can see that we are substantially slower with this implementation. We are substantially slower than other similar boards for ML workloads. So the person detect benchmark, which is our benchmark for, which is for us shorthand for benchmark, which is too large to just ram into RAM. We're somewhere between a factor of 2 and a factor of 4 slower than other similar form factor boards. So the Edge board from SparkFun and the BLE Sense Nano from Arduino. Both of those are M4 devices. They're slower clocked M4 devices, but they are M4 devices, so they have some of those facilities that we lack. One thing I'm showing here is that the difference is the enormous difference that you get from bringing your model parameters and your data into RAM instead of having them in Flash. So where are the gains that are available to us? Well, stock clocks, probably a 2x there. We will qualify a faster operating point. This is running at 1.1 volts. We are very experienced with running TSMC 40LP at more than 1.1 volts. In fact, before this chip, I've never run it at less than 1.2 volts. So we will probably, there's a lot of overclockability headroom at the stock operating point. And I think we're fairly confident in due course we'll be able to deliver an operated performance point, which is, I guess, warranted. It's not just silicon lottery. It's something we actually warrant all chips will do. So I think there's probably a 2x available to us there. we're only using a single core, and I do think that a lot of these workloads will partition very, very cleanly across a pair of cores. So I think that there is very, very close to a factor of 2 available from using both those cores. And then model parameters in SpyFlash, well, I've taken the 2.7x that you get from that we see with keyword, where it's been trivial, where we haven't had to do any work. You can DMA data in Power. So you can see what you're going to do, right? You're going to DMA in the parameters to the next bit of work while you're doing the current bit of work. There's certainly enough bandwidth for that. If you do a sort of back of an envelope calculation, suggests that there's enough bandwidth for that. It's just a piece of engineering work, and we think it's a piece of engineering work which will get done quite quickly. So you stack all of those up, and there's about a factor of 11 available. That's the kind of meat that we think we can get into. And that will obviously, very conveniently, 11 will take us down to 200 milliseconds. So I think probably where's our target? Where do we want to be in 6 months' time? We want to be able to do person detect in 200 milliseconds. And that's kind of why I'm excited about this as a platform, right? Because I think that it's, I just think large amounts of kind of a vindication of the large amounts of RAM, large amounts of integer scalar performance. It really is a great fit. Turns out to be a great fit. I can do a lot of dot products every second using this product. So that's kind of like where we are. That's kind of where we are at the moment, really. There we are. That's where we are today. What are the future directions for us? Well, future directions, a lot of optimization work. We will probably end up doing a lot of that. It's something that the team here is super, super excited about. They are really, particularly as new sensors come online, it is a really, really, really exciting thing for people to do. So I think that's gonna be good. Out in the community, ML-focused third-party boards are going to appear. So there's the SparkFun Micromod RP2040 is available now. So that integrates a 2040 into the Micromod pluggable module world that SparkFun have developed. Nice thing about that is that gives you access to all of those sensor peripherals that are in the Micromod ecosystem. So that's going to be great. Obviously, it's amazing that Arduino have decided, Arduino has been like it was an inspiration for Raspberry Pi very, very early on. I still remember going to a Maker Faire in the World Maker Faire in New York in 2011 and seeing a kid. We had a Raspberry Pi with us, and we kind of were wondering whether this was really going to be a thing. There'd been a lot of noise about it when we announced we were going to do it. We didn't really know if it was going to be a thing, and we didn't know if it was going to be a thing with kids. And then seeing all these kids with their Arduino projects who brought their Arduino projects to Maker Faire was really like, wow, okay, yeah, that is a thing. There is it's not just us trying to push this on people. There is going to be a demand. There's going to be something that picks up. So it's amazing to have amazing to have found a way to work with Arduino on this. This product obviously has the motion sense, the environmental sensing, and the audio side, along with the connectivity, which is kind of a missing piece. Like once you've inferred something's happening, what do you do with that? Well, if you're not going to send it out to a local actuator, you've got to get it back to the network somehow. So this is going to provide network. Super exciting. Honorable mention to RP2040 Pico 4ML, which I saw on Twitter this morning. These guys out of China who've produced something with broadly the Pico footprint, but with a camera and a display on, which I think they feel is going to be useful for this. Provided them with some samples a few weeks ago, and that's super exciting to see that. While they weren't in that set of people who we worked with before launch, they're probably going to be one of the earliest sets of people we work with post-launch. As our silicon supply comes online and we start to eat our way through the enormous backlog of demand for Pico. I mentioned optimized TensorFlow Lite. That really is 3 things: higher operating points, dual core support, partitioning between the cores, and then this streaming mode. So streaming model parameters via DMA in parallel. And I think the way we've set the bus up on the device gives us a good chance of making that work quite smoothly. It's been interesting talking to the TensorFlow Lite team, is that there are other this isn't just something that affects us. This idea of being able to have more control over the positioning of your model parameters in memory is a general purpose concern of other users that they have. So I'm increasingly optimistic that there isn't going to be a special TensorFlow Lite that knows how to run well on our hardware, that it will be our DMA paging stuff will be one instantiation of a general purpose TensorFlow Lite operation. Obviously, other frameworks. There's a lot of other frameworks for doing ML. Very excited to get those working. What we're hoping is that we can is that some of the work that we do on TensorFlow will then map across, will be either allow us to do work to bring these other frameworks across, or will serve as quite a nice primer to other people for how to get the best out of our platform. And then Future Silicon, obviously, there's Neil Stevenson book where he talks, somebody asks one of the characters, are you planning, I think talking about laying cables in the Philippines, laying undersea cables in the Philippines, he says, do you plan to do this again? And he says, well, business people don't like to do things once because it messes up the spreadsheets. I think it is overwhelmingly likely that there will be some other piece of silicon like this from Raspberry Pi. One thing I think there's a big opportunity here, right? Because of its need to run efficiently on processors, the TinyML world has driven a real focus on good enough primitives, right? You don't need to have some amazing transfer function that's just like ekes out a little bit more performance. It means that it's actually fairly fixed target. One of the challenges with building ASIC, frozen ASIC machine learning acceleration is that the state of the art moves forwards. The state of the art in high-end machine learning moves forwards a lot, and all it takes is somebody in a large company's research organization to discover some new trinket that gets a little tiny bit more performance out, and suddenly your entire ASIC you need to respin your ASIC. You've got to spend millions of dollars to cut a new mask set. The interesting thing about this world for us is it is a very static world in terms of what the primitives look like. So there's a little bit of research interest at the moment in what you can build in the way of a slightly better implementation. Something that really actually probably has no more arithmetic throughput than a processor core, but doesn't have all of the scaffolding around it, doesn't have all of the additional area associated with the core, and then when you're programming, it doesn't have all of the additional instruction cycles associated with get data from memory, multiply things together, put data back in memory. It doesn't have that. It doesn't have that overhead, so it can just sit there and it can have some supply of max, and it can feed that sort of systolic engine kind of thing, has a supply of max and can keep them fed with effectively fixed function memory access logic. So I think you might see something from us in the future on this. And really the goal there is not to push things forward by a factor of 100. One of the really inspiring things about this community is to show what you can do with relatively small amounts of performance. It's really to push things forward by less than a factor of 10, but to free up, with very small area footprint, and to free up other resources on the chip, to more programmable resources on the chip, to do the things they're good at, which is running general purpose code. So I think there'll probably be a little bit of work there from us, and I wouldn't be surprised to see that find its way into a future piece of silicon. So that's us, right? That's Raspberry Pi met TinyML and discovered we weren't too bad at it. So that was a fun story.
Well, thank you so much, Eben. It's really fascinating to hear how this is all starting, and kind of witnessing the birth of a new platform. And I think we've got a ton of questions that we can talk about from our audience. I wanted to kind of jump the line and ask one of my own first, though. So my question is, if there are people in our community, in the TinyML community, who want to get engaged with this work of porting frameworks to your platform, figuring out how to apply some of these optimizations, figure out how to get the most out of the hardware, what's the best way for people to engage?
I think a good way to always engage with a Raspberry Pi is to come engage with us on social media, because that's where we spend a lot of our non-engineering time. Come engage with us on our forums. There is a Pico, the Raspberry Pi forums at raspberrypi.org. There is a Pico and RP2040 dedicated forum on there, so it's a good place to engage. Come find us on GitHub. Obviously, we have forks of various useful projects that are handy starting points. But we're kind of everywhere. There is something of a backlog of hardware. If people, we do have a little occasional little stash of boards. So if there really is a compelling reason why someone would love to be working on this but physically cannot get the the hardware. Probably the two pieces of advice are, yeah, come find us on social and tell us what it is you want to do, or buy from UK distributors. It does seem like the UK distributors at the moment have pretty good stock, possibly because we can. Wow, people are allowed to rate me. That's fun. I'm going to rate myself very highly. I am out. Yes, I am outstanding. Hosts and panelists can't vote. That's sad. I can't read. I'm outstanding, but I can't read the red text at the bottom that says hosts and panelists can't vote. UK distributors, because partly because we can't, partly because we can resupply them quickly because we're physically near them, often have stock. So go check out Pimareni maybe, or in a week or so's time, go look at some of the products that are available at SparkFun or Adafruit, who will have their products in the field very soon.
Excellent. So now let's do some questions from our audience. So we saw some of the ML applications that have been benchmarked so far. Are there any others that you're aware of, or are there any particular things that people who are interested in running benchmarks can explore?
Well, I'm going to come to this next talk, actually, the talk on the 16th with a gentleman from Harvard. I'm going to be interested in that. One of the challenges here is, we're really new to this, so we don't know what to do. So I'm going to come along to that and find out. I think we suffer from not knowing what we're doing. A lack of domain knowledge. Also, I think we suffer from the lack of input data at the moment. But I'm going to be. People do amazing machine learning stuff with big Raspberry Pi. It's like my favorite one's always the cucumber sorter. There's a chap in Japan who trained his parents have a cucumber farm, and he trained a big TensorFlow model to recognize the different grades of Japanese spiny cucumber and sort them into boxes for his aging parents on their cucumber farm. But they're kind of great example. All of these are wonderful examples of how you give people tools and frameworks and power and performance and interfacing and storage, that people use them in ways that you could never have imagined. So that's a fun one. Another great one's, of course, the predictive maintenance one, and that may be one where I think we, because of our low power footprint on Pico, we may see some stuff. Sit next to a machine and listen to it. Sit next to every, put one of these next to every machine in your factory and listen to it, and then when a machine fails, go back and mine the historical recordings of the sound to see if you can find out what was predictive of failure, and then in the future run that model to encourage you to do predictive maintenance on machines. That's the thing people do with big Raspberry Pi, but it may be that with the lower cost and lower energy footprint of Pico is well suited to that.
Awesome. Would you think it's fair to say that our little TinyML community is already having an impact on organizations like yours that are deciding kind of the future of how people engage with silicon?
Yeah, I think it is, because I think that it's one of those ones where you can kind of take quite often you kind of take this big loop out through, because we're technologists and we like the high end, right? And you kind of take this kind of loop out into this exotic, high end, expensive, energy consuming world. And then you actually find that the real applications are much closer to home. We spent a lot of time pushing forwards the performance of big Raspberry. I've got about a 40x performance delta between Raspberry Pi 1 and Raspberry Pi 4, Raspberry Pi 400. Spent a lot of time on pushing its performance forward. And then we launch a platform that is a bit less performant, actually not that much less performant in terms of MIPS than a Raspberry Pi 1, and all of a sudden, that's where interesting stuff is. That's where interesting stuff is happening. So yeah, I think it's always important to have reminders that our instincts take us off in the wrong direction as technologists often, and to have communities where people can remind each other of that and sort of share some of their experiences and try and pull people back a little bit towards the middle ground is good.
Yeah, exciting stuff. All right, so the next question, it's a little bit of a religious question, I think. So the question is, why did you pick
political question instead?
It's about as political as you can get in this space. Why did you pick micro USB instead of Type-C?
I think there's a quote from I forget now, I don't know my American politicians probably, but it was I think it was one of Bill Clinton's Treasury secretaries that says when he gets reincarnated, he wants to come back as the bond market because it's the only thing that can humble the government of the United States if it wants to. If I come back, I want to come back as USB Type-C because it has an amazing brand. And people spend their whole time asking, well, we launched Raspberry Pi 4. People said, why have you used micro HDMI? So we do use USB-C for our power on Raspberry Pi 4. People are like, why have you used micro HDMI for your video data? It's like, well, we didn't think rather than USB-C. It's like, well, you can't actually use USB-C for the thing that we've done. And it didn't seem controversial to us to use a display connector to carry display data, but it has an amazing brand. You don't need it. It's bigger. It's physically larger. I think it wouldn't have worked with our mounting hole configuration at that end of the board. It's more expensive. Doesn't bring any advantages if all you want to do is run USB 1 over it. There's a sort of notion that it might be a little more robust in terms of insertion cycles, but I'm not really sure that's actually true. So it would just have added kind of cost and size to the product. Some people have used it. So Tiny2040, which is the Pimoroni product, so really the first of the this kind of postage stamp size 2040 board that launched last week, that uses USB-C and actually works really well in their form factor. But it works really well because they made other form factor decisions in the design which aligned around it, and also it's a more premium product. It's got a NeoPixel on it, so it's more premium product. So it has a little bit more fat, a little bit more cost fat that they can use to pay. I think even for us, when we buy a lot of USB connectors, it's probably a factor of 2, factor of 3 in terms of cost.
I'm sure that won't quiet the dissent,
no.
But
the people who are fans of USB-C, go look at TI's line of protection packages that they do now. They do a protection ICs. The thing about USB-C, when you have high-speed signals on it, is that the power lanes are adjacent to the high-speed signal lanes. So if you have a loose socket or you get some grit in there, and particularly if you've negotiated higher, because of course you can negotiate high voltage, you can negotiate 20 volts over this design, then you twist the connector in its socket and you have a bit of grit in there, you can put 20 volts on your fragile high-speed transceivers on your SoC. And so TI do packages that are designed to basically sit in the way and go, oh, and save your $20 AP from the grid. It's not the messiah of connector designs. If we go back to religion, it's not the messiah of connector designs. It's a bit of a naughty boy.
All right. Okay, on to less controversial topics, maybe. Do you have a plan to try a RISC-V architecture in the future?
It would be fun, right? I mean, we don't have this thing predates, this design predates the existence of exotic things like, available RISC-V cores and Cortex M33 and other things that people are super excited about these days. So it's not necessarily a positive design decision not to use RISC-V. The ARM ecosystem is really compelling advantages. The cores are really good. The tools are really good. Everyone knows how to program them. They don't add a vast amount of cost to your design. It would be fun to do RISC-V, but I think it would be fun because it's fun. It wouldn't be fun because it would let you, try to only do things because they let you achieve things, because they let you achieve things you couldn't otherwise have achieved. And I don't think that putting a RISC-V core in would let us achieve something new. It might be fun, and we have been known to do fun things. But yeah, no plans at the moment.
Cool. All right, so a few questions came in about connectivity and how that fits into the whole picture. And that's an interesting thing with embedded ML, because sometimes embedded ML means you need less connectivity. And in other ways, if you're shifting around model weights and stuff like that, it can mean that you need more. So yeah, how does that factor into the whole design of the boards and chips?
So it's a partner. We have the 2040 Connect here on the screen. It's a partner thing at the moment. We are aware of the ask. We know that people would love to have connected device, and obviously we do make other connected devices. It's deeply non-trivial from an engineering perspective to add connectivity to a platform. I'm super impressed that with the speed at which the Arduino guys have been able to do that with their design, and I'm looking forward to getting all of these in my hands, because I think it will, along with the sensor package that's on there, it will let you do things that you can't do with a Pico. Will we do something in the future? We may well do something at some point in the future, but right now we're very focused. We've seen a lot of demand. We've taken over 1 million orders for. We've shipped about 300,000 Picos. We've got about 700,000 units on backlog. So we're right now kind of just heads down figuring out, particularly in this very interesting year where semiconductor supply chain is very constrained. We've kind of got our heads down a little bit, just figuring out how to ship the unconnected device. And probably we will try to get ourselves, before we even think about connectivity, we will try to get ourselves to a point where that's in it's in Pico's in stable supply, and B, the silicon is in stable supply, at least to the close-in guys, the pre-launch customers and one or two others, but preferably to everyone, because actually we do want everyone to play with this platform. We do love it. We think we've made a great thing, and so probably that's going to be the focus of the organization for at least the next 12 months. And that will probably, hopefully, once that silicon's out there, as it already has with Arduino, once that silicon's out there, it will generate not just one, but 10 or 50 different connected devices, devices that are connected via LoRa, devices that are connected via cellular, devices that are connected by Bluetooth or Wi-Fi or Zigbee or whatever.
Fantastic. All right, so we've pretty much come to the end of our allotted time here. I wanted to throw in one last question from the audience, which is around development tools. So, what type of development tools do you think are going to make sense for this platform, and what are you thinking in terms of embedded ML development specifically?
Yeah, I mean, so in terms of the platform, what do we think makes sense? We believe very strongly that beginners should have access to high-level languages. So we are a MicroPython shop. We work very closely with Damien George, who developed MicroPython, to get a good MicroPython on the platform. So we believe that that's the right introductory platform. And actually, we're very focused on making sure that ladder goes up a long way. So it's always been the case that in MicroPython, you can write some ARM assembler. You could also write PIO assembler. So if you want to build you can actually have a MicroPython program that creates a soft SD card interface and streams data to and from it. So we've worked very hard on that. Then we have the kind of baseline C SDK where we've kind of built, we haven't ported anyone else's C SDK, we've built our own C SDK that is well tuned to our device, and we think that's our job as a platform vendor, is to make a C SDK for our own product. But you already see other third-party frameworks coming onto there. There will be an Arduino. There'll be an Arduino port. The existence of the Arduino port kind of implies the existence of some Mbed OS tooling for the platform. There'll be some other RTOS work going on, so probably free RTOS work going on. So there's a whole kind of C ecosystem that's about us providing the underpinnings. And then again, it's back to the thing about the engineering philosophy, right? Provide the middleware, provide the lowest possible level, and really we'll have limited engineering resources, throw all the engineering resources there. Tools for machine learning. I mean, the challenge is always to help people generalize examples to real world applications without being an MLG. And as it's a problem with any discipline like this, where you have a lot of very, very talented people who have very deeply thought into it, to remember 99% of the people who are going to use this stuff, develop for this stuff, once it's successful, are not going to be that sort of person. And really, it's about trying to find a way to bridge that gap in a way which is more subtle than just the canned models world. The canned models world is an unsatisfying world, so you want to try and I think it's an unsolved problem in big ML, and it's an unsolved problem in big AI ML, and it's an unsolved problem in the tiny world as well. But it'll get solved. It always does, because there's a lot of money or kudos or other good things available to the people who solve the problem. Right?
Yeah, and I have to say that we already have community members on Edge Impulse who have trained models in Edge Impulse and then ported them to Pico. So super exciting.
Really? There you are. That is good. That's really good news.
Very cool. There's some tutorials online, I think. But yeah, with that, I think thank you so much, Eben, for your time. And this has been a really fascinating insight into everything that's going on in the the tiny Raspberry Pi world. So thank you so much. We wanted to thank again our sponsors. So we've got ARM, DeepLight, Edge Impulse, Maxim Integrated, Kixo, Reality AI, and SynSense. And again, contact Betty if you are interested in sponsoring. So we've got a few messages from our sponsors. So ARM provide the software and hardware foundation for TinyML. DeepLight use AI to make other AI faster, smaller, and more power efficient. Edge Impulse provides TinyML tools for all embedded developers. And I wanted to say we've got a Coursera course, which we recently announced, which you can find from our website or on Coursera. If you're looking to get started in this space, it's a super easy way. I'm biased because I work here. Maxim Integrated. The new Max 78000 implements AI inference at over 100 times lower energy than other embedded options. So now the edge can see and hear like never before. Kixo's automated AutoML for embedded AI provides an automated machine learning platform that builds TinyML solutions for the edge using sensor data. Reality AI provides a host of tools for building products with embedded machine learning. SynSense builds ultra-low power sensing and inference hardware for embedded, mobile, and edge devices. They design systems for real-time, always-on smart sensing for audio, vision, IMUs, biosignals, and more. Our next talk is going to be from Vijay at Harvard. Really great guy, really great speaker. Definitely worth attending there. It sounds like Evan's going to be there. And that's going to be on TinyML Perf, which is deep learning benchmarks for embedded devices. So that's always at 8 a.m. Pacific time. And if you want to talk, please drop us an email at talks@tinyml.org. And that's it. Thank you so much, everybody, for attending. Thank you so much, Evan, for presenting. It's been great.